Hello. But what's up? It's Thor. I don't know what he wants. Or he probably wants me to sit next to him while he's eating. Okay. We are not officially starting yet. I think we have 5 minutes left until the official start time. I couldn't set the stream to 20 past. It had to be 15 past. But you know, that's okay. So I'm gonna hang out for a bit. Okay, this segment is going to be weird because I'm going to talk about a few things I've never talked about before during my math class, and I'm not fully confident that I'm going to be able to talk about it. We'll see how it goes, I guess. It's going to be a bit of an improv. I guess most of mine are improv, but at least I've talked about the previous things before. Hey there. Hey. Come on, buddy. Come on, buddy. Blip. Really? Just wanted to tell you you're my personal heroine and role model. Thanks. A little bit terrifying, but also very nice of you to say. I'm happy I'm able to inspire you somehow. Okay, Thor. Okay. Mistro Bistro. Where are you going? Yeah, that's the camera up there. Okay. Hey, don't tip the entire microphone. Where are the Thor emotes? You know, I don't know how emotes work on YouTube. I haven't looked into it yet. I usually don't stream on YouTube, so. Okay, there. I think the camera is picking up the wrong thing. You're supposed to focus on the cat. There we go. How are we doing on time? Starting soon. Starting in 2 minutes. Okay, Thor. Where are you going? What's your plan? Is that your plan? You wanna be in my lap? Thor, don't show your butt to stream. That's inappropriate. Yeah. That's inappropriate. Okay, Thor. Okay. Bistro. Okay. Let's see if we have some students. All right. Please react. If the students are here, then do react and show your presence. Thor is also here. He's showing his presence all the time right now. Okay. Hey, Thor. I need to start my math class. Yeah. I need to start the math class. What's your plan, buddy? Yeah, I need to do math. Yeah, that's the pop filter. Boy. Okay. This is the stream now. Thanks, Thor. Can I start my math class? Thor? You're slobbering all over my microphone. Yeah. Think of the students, Thor. You're delaying. Yeah. What are they gonna think when you're holding me up like this? Which breed was Thor again? Oh, Thor is not of any specific breed. Ashley got Thor from a shelter, and so he's just a regular old mixed cat. Just a little guy. This is true. That is Thor. Yeah, he's long-haired, tuxedo cat. He's also American, so he moved all the way from Seattle to Sweden. That's this boy. Okay, do you have a plan? Are you settling here? Okay. All right. There we go. You did it. Oh, you did it. Okay, now we're ready to start. Okay. All right. We got our Photoshop. Just gotta check that I have my Unity. Okay. Cool. I think we're ready to start. Everyone's present. Sorry for the Thor interruption, but you know the law. You can't move cats. They have to move on their own. Okay, so this is our bonus session. So this is where you can, I imagine we can just talk about whatever you want to talk about. So if you have a question about things that are probably not related to what we're talking about, that's fine. It's okay to go on a bit of a tangent, because this is kind of all just bonus optional content, I guess. I think of the topics that we listed, it was either procedural animation and easing functions, and splines, and more abstract algebra. Those were the three things. I think the procedural animation, I think, is probably the most useful part of this, and splines. So I think we should start with the easing functions, and then we can go to the more abstract algebra later. I think that's good, just to make sure that we have time to cover the more important things first. So the again, abstract algebra and whatnot is less useful in game dev. It has a context and it has a use, but it's more rare. So I think we should start with easing functions and procedural animation. Yeah, all right. And so I think we should start with something that needs procedural animation. We're going to start with something that looks bad, and then we're going to make it look good. I think that's the starting point. And so we're going to make a new script. We're going to call this grid cube. All right. Okay. So we have our grid cube, and it is somewhere. It doesn't even have a cube. That is very rude. So let's give it a let's just create a cube as a child object. Okay. And let's switch to 2D. I think that makes it a little bit easier to see. Wait, using middle finger for scrolling seems illegal? Wait, why is that illegal? Wait, what do you use for scrolling? Is there a different option? Just gonna create a material that's a little bit easier to see, because now it's kind of hard to see. Index finger? What? Why would you use your index finger? You guys don't? No, I think you might be alone in this. As we've just discovered. I mean, I think I don't use my ring finger to right click. I usually swap with my middle finger between these two. Because it's very rare that I use them at the same time. So too late to ask about the lecture before lunch? Maybe? I don't know. What do you want to ask? Try it. See what happens. Okay, I was just setting up this little grid cube thing. We're gonna call this cube. I'm gonna modify this script. Probably should have done this off stream. Okay. So, I was thinking we would start with a script that just moves a character. In this case, it's just a cube. Moves the character based on input from the keyboard. So we're gonna make our old trusty update loop. Why is it so dark even though my material is a bright yellow? So if you want to make it very visible, create a new material and set the material to, or the shader to unlit color. Unlit color makes it so that you don't have to, then it's going to be the color you set it to. And then you might also be able to just toggle off lighting in the scene, and then in the scene view. And then I think it'll also look better. Okay. So now we're just gonna make a very basic movement code. So we're gonna have some key that you press, and then you need to move in some direction. All right, and so we're gonna do transform dot position, or rather, if you press the key. Right there. So get key down. If you press this key, we want to move the transform in the direction of the direction here. And then we just add all of our keys basically. So you can call this check move. There we go. I need a drink. Okay. So check move, keycode.w, then we want to move in vector2.up, duplicate that, and then we have s, and then we want vector2 down, a, vector2.left, and d is vector2.right. All right, now we have an extremely basic movement system, right? We press the key and then we move in that direction. We just immediately snap to that position. Okay, let's recompile. And now if we hit play, right, we set it to equals. We should do relative, so we should do plus equals. I should also disable the turret because it's kind of distracting. All right. There we go. So now I can press keys to move this box. This is like the hello world of player character movements. Okay, but this looks kind of, it's snappy and responsive, but that's kind of all it is. It doesn't look very smooth. It is very kind of basic, right? And so what if you want to add smoothing to this? And what if you want to add a custom smoothing to this instead of just having a snap movement or just like a lerp smoothing or whatever? Now we talked about that earlier. That's the kind of smoothing where you're exponentially approaching some value or asymptotically. Asymptotically? I forget. I don't know how to pronounce it. And so you kind of approach your target with this like infinite fall off. But there are other ways that we can do this type of smoothing. So that is kind of a whole universe of a topic, which is all about something called easing functions. And so that's what we're going to look into now. And so first off, we want to make this movement be smooth. We want this to be, or rather, we want it to be continuous because now it's completely discontinuous. In just one frame, we just jump to a new position and then we're there. But what if we want to animate from point A to point B? So let's do that. So let's make a, we can make a bool for is animating. We need a vector3 for the target position, and a vector3 for start position. Or maybe position start, position target. All right. So we're gonna set up some state here. So if we are if we're not animating, then we're going to check for input. So we can just scoot that over to a function. All right, and then we have our animate function. And we can also flip this. Okay. All right, so we're also going to need to know when we started moving. Actually, we don't super need that value. We can call it move time. I think that's good enough. All right, and so in our animate function, this is where we want to animate from the start position to the end position. So what's going to happen is that when we press a key, we are, instead of just setting the position directly, we're going to set the start position of our movement. We're going to set that to transform.position. And then the end position, or the target position, is going to be position start plus our direction. And then we're going to set is animating to true. So now we're going to start an animation. So pressing a key will set these parameters and start the animation. Okay. And then we're also going to have to set move time to 0. This is the time we've spent moving. Okay. So in our animate function, first we're going to have to increment the time we've spent moving. So we're going to do move time plus equals time.delta time. So animate is going to be called every frame. We might want a different name for this. What do we call this one? This should be animation time. That's better. And these are all going to be private things. We don't have to expose those. These are just, this is just for state, right? And so we can make a header. All right. Actually, that's not even visible, so I don't know why we're making a header. There we go. That's a header. All right. And now we want to make this smooth interpolation from the start point and the end point. And as you know, we can use vector3.lerp to interpolate from point A to point B, right? In this case, we want to interpolate from the start position to the target position. And then the t value is going to be the percentage from start to finish, right? And here's where it gets a little bit trickier, because now we only have time since the animation started, but we need a t value. And that depends on how long we want it to take to make a single move, like move a single grid unit, right? And so maybe we want a public variable for that. And that one we're going to call move time. That's how long it takes to make a single move. All right, so how long do we want that to be? Maybe we can make it, in the beginning we can start with 1 second, I suppose. All right, so now that we have the animation time, the time we've spent animating, we can convert from the time we've spent to a t value for the total duration. So we can do math dot, or actually we can just multiply it directly. We can do animation time divided by move time. And that gives us the t value. And we might also want to clamp this between 0 to 1. So this gives us the percentage of the movement animation, right? Oh, the weird person is back. Okay. Kukulorokel, you need to stop spamming the chat with just garbage. There we go. All right. So we want to interpolate from the start to the target, and then we have our t value here. And that's going to be the new position for our objects. Then we also need to be able to stop the animation. So in other words, we know that the animation is finished if t is equal to 1, right? So if t is 1, because we're clamping it, it doesn't go above 1. I guess we can I guess we can do this to avoid the warnings in Writer. Then we need to stop the animation. So then we just do isAnimating equals false. Okay. This should give us a very, very basic movement animation. So let's see if this works. Did any of you bring beer for this last session? I know I encouraged it, but... Okay, there we go. We have our very basic movement. You can press a key, and it kind of very sluggishly, slowly, like, drags itself across the board to hit the next square unit. Okay, and so now we have our very basic movement. We might want to make this faster, so we have the movement time here. So I'm going to change it to 0.1. And so now we have a much faster movement. I'm going to slow it down a little bit so that it's easier to see, to tell what's going on stream. We only have so many frames to work with. So I'm going to set it at 0.4. And there we go. Here's our basic animation, right? But this doesn't look super nice. Like it's very linear. It's kind of like we immediately start moving, we immediately stop. It looks very, very jank, right? And this is where easing functions comes into play, because this is where we might want to modify the t value so that we can add some sort of smoothing or basically make a type of animation and define that path over time. And so here's where we can actually make use of our old friend Desmos, as usual. There we go. Okay. So the current function we have for our t value is just the this is kind of the identity function. This is the function that just returns the input value, right? So this is what our animation looks like right now. We can also restrict the range so that we just see the relevant interval. So there we go. So this is our animation right now. The x-axis is time, and the y-axis is is kind of also time, but it's the time we might want to change afterwards. And so remember, the y-axis is the output. Thor is poking plastic. And so here we can kind of start playing with like, okay, what if we change this this animation? So what if we do? Let's see. Let's do this instead, and then we hide that, and let's see. Okay, we can use that. Okay, so if we have t, this is our regular old like straight up lerp, right? But what if we multiply t by itself? We square t. Now we have a different curve, right? So this one, it looks like it's, remember, x-axis is the input and the y-axis is the output. So in this case, it's actually slow in the beginning. So because if we move linearly here, you can see that the vertical movement is pretty slow, and then it's going to speed up near the end, the closer to 1 we get. And this is a very, very basic type of easing function. So usually when it's slow in the beginning, then you would call that an ease-in function. So we can actually implement our very first easing function. So maybe we can do float and call that ease-in. and then we have our t value here. And then we just do t times t. So this is the function that we just did. So now we can apply an easing function here. So we do t equals ease in t. And then let's see what happens. Let's change the move time again. All right, let's see. Let's go. So now you can see that when I press, it actually starts slow, and then it stops very suddenly. And that's because that's the easing function that we just used. We told it to start slow and then stop suddenly. And that's exactly what we're seeing here. Start slow, stopping suddenly. And we can kind of play with these functions however much we want. We can define whatever math function we want here, right? We can type literally anything. But the crucial thing is that usually for easing functions, you generally want easing functions to start at 0 and end at 1. So start at time 0, y value 0, and end at the time 1 at value 1. Will it be accelerating if you hold the button longer? No, this is a predetermined animation. You press a button and then it plays. So I'm not holding any buttons, I'm just tapping them once. Okay, but usually you want something called an ease out function. This is an ease in function, but for character movements, you usually want it to be more responsive. You want the first input to like really, really start off quickly, and then you want it to slowly settle. And that you can also define. We can do 1 minus t squared, and then we negate that. So now we have an ease out function. So now this is kind of the opposite of what we had before, right? So this one starts fast and then it slows down. That's usually the type of movement you want for this type of character movement, right? When you're making like a basic grid-based movement. And so this is called an ease out function. Specifically, this is called a quadratic ease out because we have a quadratic exponent here. Like 2 is the highest degree of this easing function. And so we can rename this to quadratic ease in. Then we can make another one, which is the quadratic ease out. And that one was 1 minus t squared. Okay. So I believe this would actually be the same thing as 1 minus quadratic ease in, and then we pass in 1 minus t. So we're kind of hijacking the other easing function there. I think that's the same thing, because that's just squaring this one. Okay, so let's try using the ease out function instead. And then let's go back, recompile. There we go. Let's see if this works. And there we go. So now you can see that it starts off fast and then it slows down as we're approaching the end. And this already feels much, much better. This just feels great, right? Like you're pressing a button and it kind of slows down, and we're doing this without the weird like lerp smoothing that kind of like always has this infinitesimal like asymptotic fall off that's really annoying to deal with. And so this is just kind of playing an animation. And we can really play around with whatever functions we want here, which is really useful. And so there is a whole host of kind of standardized easing functions that you can find online. There are many of them. And so if you want to like dive super deep into this rabbit hole, you can. Should also talk about one of the more popular ones, which is this one. Except I got this flipped. Or is it minus? It might be minus. I think it might be minus. There we go. Yes, it's minus. So this one is called the cubic in-out because it's slow in the beginning and slow at the end. So it's easing at the start and at the finish. And this one is very useful in particular because this is kind of a universal smoothing operator that kind of just smooths both in the beginning and at the end. You can sort of see that it's kind of similar to the behavior you would usually get from a sine wave, right? So this would be a cubic smoothing function. Yes. Smooth operator. Yes. So this function is also sometimes known as smooth step. Although smooth step has different definitions depending on where you're using it. But yeah, so this is a very, very common one. So this is kind of the ease in out or smooth step. Sometimes people separate cubic in out from smooth step, but I would call this the canonical cubic in out. There's disagreement about what should be called what. And so this would be equivalent to 3. I guess we can separate out a t here. Can do t squared and then 3 minus 2t. So t times t times 3 minus 2 times t. This is called cubic in-out. There we go. How about exaggeration going below 0 and above 1? Yes, we can do that too. So this would be a smoothing in-out. So let's look at that first. Someone asked how expensive these are to use. They are very cheap because they're very, very like small mathematical functions. They're very cheap to evaluate. It's just a cubic polynomial. And so in this case, it is smooth in the beginning and smooth in the end. And now we just defined the smooth little movement, right? You asked about exaggeration. How deep should I go into this? So there is there's a kind of a generalized way that you can express these functions, and that kind of goes into a little bit into splines. So the general form of this type of easing function, at least when it comes to cubic easing functions, is that we have some function f of t. And then we have some constant based on t cubed plus bt squared plus ct plus d. And I can't use t here, I think. I think I have to do... Whoops. Is it upset because I've already defined t? Or oh, it's probably just because No, it is upset because I'm using t. It's upset at both things. Okay. Okay, so this is just a generic cubic polynomial, right? We have a factor of x cubed, x squared, and x, and a constant d. And there is actually kind of a general way that you can define easing functions that I think is pretty useful. So if you consider, now we just have all of these parameters, we can just freely set them to whatever we want, right? Like we have this constant and all of that stuff. And so there's kind of a useful way to parameterize this that I think is kind of cool, where maybe we want to set the because we want the start position to always be at 0, 0 in this case. In order for that to happen, the constant has to be 0. So the constant factor. So we can actually remove d immediately. And then we want the endpoint to always hit 1 here. In other words, we want the function, when we evaluate this function at the value 1, we want it to always pass through here. And so we can actually set that constraint up. If we replace x with 1 here, then we're going to get an equation that looks like this, because x, like 1 to the power of whatever, is just 1. And so now we have a relationship here. We have a relationship of a plus b plus c must equal 1 if it is to pass through this point. And so what we can do is that we can define c in terms of a and b. So we do 1 minus a and minus b. So we're just scooting that over to the other side. So now we have c equals 1 minus a minus b. And then we remove the constant. And now we have fully constrained this function to guarantee that it will always pass through those points. Because we just mathematically told it to always do that, right? And so now we can actually just kind of tweak this however we want to make whatever kind of easing function we want, right? So this kind of looks like an in-back function where it like exaggerates a little bit and then it speeds up toward the end. And then you can do something like this, and now we have sort of a similar situation there, and so forth. You can also then we can also define this in terms of the derivatives. So maybe instead of using a, b, and c, maybe we want to use like, okay, I want the derivative at 0 to be this, and I want the derivative at 1 to be this. And I'm just going to open another graph because I've done that before, and I don't want to. I want to spare you the math because it might take a while to set that up. Okay, I'm gonna have to search. It's somewhere here. Where is it? Where is it? Did I lose it? Oh no. I'm not seeing it. It's supposed to be called like Hermite easing or derivative easing. Oh shit, I should have prepared this. It's over. Okay, I guess we could derive the math. Or I think I actually have this in my notes. Yes, here we go. Hell yeah. So you can do the math to figure out how to do easing with derivatives. So we can kind of re-express a and b to basically just set the derivative in the beginning and set the derivative at the end. And then we kind of solve for what constraints that give us. And so this is the equation that pops out. And so this is also just a cubic equation. So just replacing these. There we go. And let's restrict the range. All right, actually, let's not do that. And so now what we're setting here, the two variables we have is the slope or the derivative. So if both of these are 0, we get the cubic smooth step function. Like this is smooth step straight up. But maybe we want to tweak the derivative at the end to be either positive or maybe negative. Or maybe we want to tweak this one in some way. So there are many different ways we can do this. So if we tweak this one like this, now the derivative in the beginning is pretty extreme. It's a pretty high value. And so now this one is going to overshoot and then settle here. And so this would be an ease out back function, which is kind of a nice way to parameterize kind of all of the cubic easing functions can be defined in terms of just a and b in this case. So it's kind of cool. But again, there are many different ways of doing this type of easing. And so, yeah. All right, do you want me to implement this to show what that looks like as well? Or what do you think? Maybe I should do that. Maybe I should just straight up add this function. Would that one go backwards at the end? Yes, it would. Okay, so this this is actually kind of, sort of, like a Hermite interpolation. So let's do let's call it custom ease, and then float the derivative at A and float the derivative at B. And that is this whole function right here. And so we're just gonna return that. Let's see. So dA, dB, dA, dB, dA. Then we need the input parameter, which is going to be t. So replace x with t. Okay. Slap in some multiplication symbols. All right. Goat? No. So t squared is t times t, and then we have t cubed, which is t squared times t. There we go. T3, T2, this is C2. Let's just call them A and B. That's confusing. There we go. All right, so now we have our custom easing function, and we can actually express all of these in terms of the custom easing function if we want. But in this case, we are gonna do float ease out back. All right, so what was the parameters? We set B to 0 and A to 5. We can set A to whatever we want, kind of depends on how aggressive we want this one to be. But I guess if we want it to be visible on stream, it probably should be pretty aggressive, so let's set it to 5. You can make it a parameter even, if you want to. So A is 5, B is 0, and then we set the time parameter is just t. So now we have a new function called ease out back. So that one is going to overshoot. And so now we're going to have to separate the time from the position t value because we're checking if t is greater than 1 to tell if the animation is done. We need this to be the original t value here. And so we might want to separate these now. So I'm going to call this t time. And then we're going to float t value. So this is the remapped value. So we're going to use that one for the lerp. And remember, Unity's lerps clamp by default. So we don't want to call lerp in this case. We want to call lerp unclamped. This allows it to extrapolate. So we want to make sure to call that. Tea time? Is it tea time? I don't have any tea. I have water, so I'm going to have water. Thanks for the reminder. Or did you mean break time? Oh, it is kind of break time. Anyway, I'm going to continue for a little bit. All right, transform position equals lerp unclamp. We're using the output of the easing function in this case. We're still using the time to check when the animation is done. And so the time in this case is the x coordinate of our graph, and the t value is the y coordinate of the graph. Okay, and so this should give us the ease out back function. Let's see what that looks like. This should look a little bit squishier. All right, and so now you can see that it overshoots and then corrects back, right? It does a neat little overshoot. I hope it's visible on stream. You might have a lower frame rate, but hopefully it's visible. And so now it looks a little squishy. It kind of like, whoops, overshoots and then slides past, and then yeah. So it adds a little bit of a juiciness to it, which is nice. And of course, these functions can be absolutely anything. You can define these using whatever kind of math you want. And an even more useful way of doing it, which is less fun because there's less math involved, but it's more useful, is to actually just straight up use an animation curve for this. So you can just do public float, public animation curve. And then we can call that movement animation. And then we, instead of doing ease out back here, we're just going to do movement animation dot evaluate at t time. So now we're going to use an animation curve to this. We're going to recompile. Doop, 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 doop. There we go. And so now Unity has this thing called an animation curve, which you can edit directly here. And so now we've just made a linear curve, and it has a few presets built in. You can see that it has the ease in, it has ease out, ease in out, and then a few other functions as well. And so what's really neat about this one is that you can add keys. So this is kind of like more of a traditional animation workflow, where you have way more control over how you want this to behave. So this is more like the workflow for like an animator, so they can tweak this to their heart's content, to make their perfect little wobbly movement. There we go. And kind of the secret of this one is that this one, each curve is also defined by a math function. In this case, they are defined by what's called a Hermite math function. And together, all of these make up a spline. So what you're looking at here is a one-dimensional cubic Hermite spline. A non-uniform one-dimensional cubic Hermite spline, if you want to go super technical. I've been digging extremely deep into splines as of late, so I have a ridiculous amount of knowledge about splines now. But yes, so that's a spline. So now we're using the animation curve to do this animation. So we of course have way more flexibility when using an animation curve or a spline. And so now we have this very, very wobbly animation. What's Hermite again? We could go into splines if you want to. It kind of depends on how much time we have and how much you want these things. Like how much you want, like, because we also need to cover abstract algebra. So I don't know if you want to hear about splines. I think splines was the least voted on of the three main topics. But we could go into it, of course. So this is kind of just the basics of how to do like procedural animation, where we have time values in code, and then we're kind of applying them or using them either through like mathematically defined easing functions, or we can use animation curves that we've kind of that's a bit more easy to author like by hand, where you have a lot more control over what you want this animation to be like. So this is a very, very useful tool. Okay. Could you backtrack a bit on how did you make those parameters be the derivatives of each point? Yes. Yeah, we can do that. That's going to be a bit of algebra, but we can do that. Let's delete it straight up. There we go. Okay. So ax cubed plus bx squared plus cx plus d. Okay. So we know that we need we need we need it to start at 0. So we need the d parameter we can remove. We need it to end at 1, which means that that's the thing we did before. We kind of tweaked one of the values here to be 1 minus b minus a. So c is no longer required. So now we forced it to pass through these 2 points. Then if you want to make the derivatives match, we need to find what values should we use for a and b if we want that to be the case, right? So we can just write those equations. So let's define the start derivatives. Let's use capital letters for those. Or actually, let's use D0 and D1. That's a little bit more technical, but maybe that's good. Okay, and then we basically just need to do the, we need to calculate the derivative of this. You know how to differentiate at this point. So we take the exponent, move it down, reduce the exponent by 1. Same thing here. Take the exponent 2, move it down, reduce it by 1. And then this one is just a constant because x removes, is removed like that, right? Okay, so this is the derivative that we have here. So let's see. All right, and so now our requirement is that we want the derivative at, oh, maybe I should zoom in a little bit. I don't know how easy this is to read. We want the derivative at 0 to be equal to d0, right? In other words, this function, let's call it f prime of x, when this is 0, this should equal d0. So we can simply write this function equals d0. You can kind of ignore the graph for a while. And then we solve for one of the variables. And x in this case, we know that that's 0 because at time 0, we want the derivative to be d0. So x is 0. So every term of x disappears here because we multiply them by 0. And now we have the value for d0, just kind of straight up, right? So now we know that d0, or no, sorry, we're not solving for d0, we're solving for a. So let's undo that. Okay, or solving for b. We can solve for either of them. So if we want to solve for b, then we need to do, we need to subtract 1, and we need to add a to both sides, and then we negate both sides. So we multiply both each side by -1, so that's going to flip all the signs. So we're going to just flip all of those, and now we know the value of b. And so now we can actually remove this b slider because now we've calculated the value there. And now we can set d0. And so if we set it to 0, the derivative is flat here. We increase it, we have a positive derivative. If we do negative, we have a negative derivative, and so forth, right? And then we can just go through the same process, but for the derivative at value 1. And so we do that, and then we say that this should be equal to d1 when x is 1. So replace x with 1. So all of this is just going to get multiplied by 1. And then we need to solve for a. But in this case, we have a few unknowns here because b, we should replace b with this equation here. So we're going to do a substitution. And we can actually simplify this a little bit because now it's a little bit messy. So we have 3a minus a is going to become 2a. 2b minus b is just b. And there we go. And then we know that b equals this, so we can just substitute b by that whole formula. So now we have, let's see, we have d1 equals all of this, so we subtract another a, so that becomes just a, and then plus 1 is plus 2, and now we can solve for a, right? So we add d0 to both sides. Oops, that's multiplying. I don't want to multiply. And then we subtract 2 from both sides. And now we've defined both a and b And now we can remove the a variable, and there we go. So now we have the function where we set the derivative at the start and we set the derivative at the end. So this is, again, you kind of like, you set up your constraints and then you solve for the unknowns. And that's exactly what we did in this case. And so yeah, we set up the 4 constraints we had was, just to clarify this a little bit more. So the 4 constraints we had our graph, right? And it goes from 0 down here to 1. So the constraints we had were when at 0, we want this function to return 0, right? At 1, we want this function to return 1. This pins it to these 2 points. This forces the function to always pass through these points, right? So if we apply these 2 constraints, that's what's going to happen. And then the second constraint was that we wanted the derivatives. In other words, f prime, the rate of change at 0, this should be equal to d0. And then the rate of change, in other words, the derivative at the end, should equal d1. So these are 4 constraints, right? We have 4 equations that constrain the whole curve in a different way, right? And then an appropriate function for this is the cubic function, because we have 4 constraints. That means we need a math function with 4 unknowns. And that just happens to be the cubic in this case if we want to use a polynomial. So ax cubed plus bx squared plus cx plus d. So in this case, we have 4 unknowns, we have 4 equations, and then we can just solve for that. We can just straight up work out that equation, because each of these constraints allows us to express each of these in terms of the other variables. So this is just kind of basic like equation solving. And so that's what we did for this easing function, where again the derivative is the slope. So what we have control over is we set the slope here and the slope here, and then it kind of solves it for us to set this cubic polynomial to match that range based off of the values that we choose. If both of them is 0, we get the classic like smooth step function. All right, so that's what happened. I took a bit of a shortcut. I did these first, and then I hand waved the other 2, but now we did the other 2 as well. Okay, algebra. Imagine that. All right, that's what we did. Any questions so far? There's been dead silence from chat for the most part. Don't suppose you could get the value of the curve and build a road on that instead of creating our own Bezier? You can do that. You can define whatever function you want. So you can totally do that. Just vibing. Okay, that's good. All right. Typing. Oh yeah. Someone asked if there's a name for this. Yes. So this is called cubic Hermite interpolation. In this case, it's specifically one-dimensional interpolation. And we've also, instead of having custom values here, we just have specifically 0 to 1. But you could set custom values here if you want to. So if you wanted this to be, I don't know, value 1, or sorry, value 0, and value 1, then that's Hermite interpolation, or Hermite if you're French, I guess. Solving for this gives you a Hermite spline, or rather Hermite curve that you could make a Hermite spline out of if you want to. So yeah, this is the Hermite interpolation, cubic Hermite interpolation. Okay. And so the you can actually solve this the same way for 3D curves, where you have a starting point and you have an end point, and then you specify a starting derivative, in other words, velocity, and then you specify an end derivative, which again, that's velocity, right? And then it can create a curve from those two data points. And this is the Hermite curve in 2D instead of 1D. So this is the Hermite curve. I guess it's specifically the cubic Hermite curve. So you can see that this is kind of similar to the type of interpolation we did with the Bezier curve, right? But instead of specifying like arbitrary points here, we're giving it velocities. Just straight up velocities. I want the velocity in the beginning to be this. I want the velocity at the end to be this. And then it just creates a path that follows those constraints that you've given it. That's the cubic Hermite curve. And I guess this is a good segue into splines. So I don't know how much time we have. I guess we've gone for an hour now. Do we do a break, or well, what do you think? Do we just like steam ahead? Break sounds good. Okay. Let's do a break. Okay, we're doing a small break, 5-minute break. Okay. It's 14:25, right? Yeah, okay. All right. Only live on YouTube? Yes, I am only live on YouTube right now. In fact, I am not allowed to stream on both YouTube and Twitch at the same time, unless I want to break my Twitch partnership. And I'd prefer not to do that. It seems kind of pointless. So I'm not allowed to simul stream. Wait, someone make a French Freya meme? Wait. Was it because I said Hermite? Charles Hermite. I don't know how to pronounce his name. It's Charles Hermite. That's the American pronunciation. Butchering the French. So wondering why you don't stream lectures on Twitch. Is it a restriction from FutureGames? I used to do all of my lectures on Twitch. I wanted to try YouTube. I just wanted to see what is the audience. Maybe I can pick up some more people than on Twitch, or maybe less people. And I just wanted to see what the audience was like. And so it was a bit of an experiment. And so that was why. I was just curious to see how it would work out. And yeah, it's been an interesting experiment. I definitely have much less viewers than on Twitch. Usually on Twitch, when I do these streams, I tend to get like 200 to 250 viewers. And so I usually get more viewers on Twitch. I've noticed that during these streams, the first one I had a lot of viewers because I kind of tweeted about it a lot. But then for the consecutive ones, I kind of stabilized at like 90, like 80 to 90. And so, yeah, which I didn't really know what to expect. Either it could be the case that my YouTube audience is not following me for live content. And so maybe I just don't have a lot of people watching my live stuff on YouTube. Or it could be the case that maybe YouTube's algorithm would push my streams so much that I would get way more viewers than I would expect. Either of these could happen. Yeah, so it was an experiment. I don't know what the answer is. I just know that I have less viewers, but I don't know why, and so it's kind of hard to figure things out. I guess I would have to check how many people. I guess I would have to check how many of the viewers are my followers or subscribers on YouTube versus how many new people are coming in. Do you have the same amount of weird backseat teaching on Twitch, or is it less more there? I have more viewers on Twitch, and so there's more backseating on Twitch. So it's worse on Twitch, but that's probably just a like factor of the number of viewers. Oh, I'm talking concurrent viewers, William, not total amount of views. So concurrent viewers is much higher on Twitch. Yeah. Yeah, you can see people quitting after each video. They got tired of it. Okay. Backseat math teaching is such a strange concept. I think a lot of people want to inject more information. They also want to come across as knowledgeable and smart. So I think a lot of people just kind of do that. And sometimes it comes off as a little bit weird. Because the thing is that like, so quite often when I talk about say the dot product, like the beginning of our lecture, I have a very, very, very strong focus on linear algebra. Like we do a shit ton of vector math, and we just talk about the dot product, and the projection, and all of that stuff, and matrices and spaces. I do all of that stuff without ever touching trigonometry. And this is intentional. Like this is something I'm intentionally doing. I'm intentionally withholding information in order for us to focus on that later, right? But every time I talk about the dot product and I write this equation, every single time people on YouTube go, talk about the cosine. Talk about it's also the cosine of the length of the two vectors. You need to mention the cosine. Don't forget the cosine. And I'm like, shut up. I know. I'm intentionally leaving it out. Stop flooding my narrative with spoilers. We're gonna get there later. Just chill your beans. And so, yeah, it's a little bit frustrating when people like, I don't know. Sometimes it feels a little bit like they're putting, I don't know, railroad track in front of me, and it's kind of annoying. Is it that bad to spoil stuff with math, though? I mean, if you are in a lecture where you're going to talk about that later, it can be distracting, right? Because you're not supposed to, like... I've designed the order that I talk about things very specifically. And so I don't want that to get distracted and distorted and messed up, right? But otherwise, if you're just learning math and you're okay with just random information, then of course it's good to just, I don't know, have random information available to you. But in my case, it's a little bit annoying when I'm like specifically trying to have a narrative thread to it all. Okay. All right. yeah, I don't know. Like, to me, it is spoilers. I don't. Yeah, I do see it as spoilers because I do consider the narrative thread of at least the things we talk about from the first few lectures. But that might be a flaw in me, but I think it's the best way to go about it. But I don't know. I don't know. Or I'm just grumpy that people are backseating, and I'm trying to come up with excuses as for why I'm grumpy. Okay. All right. Oh, is Christian not doing assignments for you? Maybe he isn't. I actually don't know. I just thought he would. Oh, that's in part 2. Oh, nice. Okay, then I don't have to do anything. I don't have to send part 2s. It's always good to ask Christo though. Get clarification on how the assignments are going to work out. Okay, just had to ban someone from chat because they were really distracting and weird. Okay, all right. Should we resume or should we wait for? Should we wait for Christo to respond, or should we just steam on ahead? Teaching to a body of students with wildly varying levels of math knowledge is difficult too. Yeah, it is hard. Some of us have degrees, some of us have met a triangle once, but it didn't phone back. Yeah, sadness. And then there's also people who did go to school for that stuff and then forgot everything. I think the strategy that I usually go for is that I have a pretty fast pace, and when I talk about the basics, I try to bring in different perspectives and contexts that make it interesting even for those who already know those things. That's usually what I try to do. Just not to bore the people that are like, oh, I already know the dot product. And then I try to add more context to it. Whether or not that works, I don't know, but I hope it does. I think it does. Okay, we're off break. We're resuming. Okay. Show your presence. React. What is a long cat? I'm uncomfortable by this long cat. All right. Oh, what a textbook. Oh God. Textbooks are so boring. I don't know how they fail so hard at making textbooks so boring. Oh my goodness. Okay. Let's resume. Where were we? We were talking about Hermite curves. All right, let's see. It is 14:30. All right. I think I can briefly talk a little bit how splines work, and then we can continue to abstract algebra. How does that sound? I think the splines, we don't have to go super deep on it. I can sort of kind of just explain the basics of it. And so the basics of splines is that it's effectively like taking a set of curves and stitching them together end to end. So we covered the Bezier curve before. Where is the Bezier? Here it is. So this is the Bezier curve, right? We specify a bunch of points, and it creates a curve between those points. Now, if you stitch multiple of these together, so maybe you're creating a longer path, then this is usually what we call a Bezier spline. And so you might have seen this type of control before, where you have these handles that you can drag around, and then it can create this kind of vector-based shape. And this is actually the exact tool that Photoshop uses and Illustrator uses for their paths. And so you can kind of can see how inaccurate I was. And so now this is literally using Bezier curves. Like Photoshop's pen tool is a set of Bezier curves stitched together. So this is just cubic Bezier curves. You now know the math to write this. You can make Photoshop's pen tool using what we already talked about. You know how to make a cubic Bezier curve, and I think you would know how to stitch them together end to end, right? And so yes, you can make Photoshop. You too can make Photoshop. No need to pay Adobe. You can just make Photoshop. And so this makes a spline. Now, the topic of splines goes incredibly deep, depending on how far you want to go. And so there are many different types of splines. In that case, that was a cubic Bezier spline. You can do the same thing with the cubic Hermite curve, where you can just keep specifying velocities and points, right? You want the next point to be here with the velocity going in this direction. And then you would keep defining shapes like this. And then the cool thing about the Hermite spline is that you do specify explicit velocities, which is kind of cool. So if you want to animate something along a path, the Hermite spline actually lets you say, I want this to go this fast at this point. And so that's kind of the power of splines. And you already saw the little animation we made in Unity. So this is also a spline. We basically set the point, and then we also set the derivative. Remember, the slope is the derivative of a one-dimensional curve, and we're basically just setting the slope here. And so that's why this is a Hermite spline, but it's a one-dimensional instead of two-dimensional. Excuse me. Okay, and so where did my window go? And I happen to be working on a video about splines that I've been working on for about a year now, that I'm going to release on YouTube soon, TM. And it's a video about splines and continuity, which is a very important property of splines. So if you want to dive super deep into splines, how they work, all of that stuff, you can just watch the video when it's released. It's going to be out in maybe a few weeks. And so this is going to be out at some point. And yeah, so here's another example of the Hermite spline used for animation. So this is kind of how it works when you're animating something with Unity's animation editor. So we set up these splines that defines like the position of an object. And then you do the same thing for like the angle. So now we're animating the angle of this cube using a spline as well. Then maybe we can change the scale over time using a spline. So we're just using a spline for all of these different properties in order to animate. And this is effectively how all animations in games work. All animations, every character animation uses splines. either they use the Hermite spline or they use the linear spline, because sometimes you optimize that way. And so it's a very, very, very broad topic where there are many different types of splines that have many different properties. Yeah, and so that's kind of the whole universe of splines. It's super useful for animating objects and that kind of stuff, like defining paths and whatnot. Yeah, and so I don't know how much I should go into depth about splines. So maybe we should hop on over to talk about abstract algebra. If you're feeling ready for abstract algebra, I don't know if you do. Are you feeling ready? Are you feeling ready to just breach that subject? Not a chance in hell. Do it. Okay. Let's see. When do we have 1.5 hours, right? Ish. What's the calendar? I think that's a good amount of time to talk about abstract algebra. Okay. I might mess this up because I have never done an improv lecture on abstract algebra before. And so I'm not sure how well I'm going to explain this. And I also don't know as much about this as I do about the other topics I've talked about. And so I'm going to have to expand the canvas. 7,000, 8,000 pixels. I don't know. Oh boy. Okay. I'm gonna need my notes later on this. All right. Completely lost. No, not the Freya spline. Okay. Let's where do we start? Okay, let's start with the imaginary number, the imaginary unit. It's a very fascinating topic. So you probably heard about this one in school. I hope you did. And so let's zoom in a little bit. Also try to keep talk about other things in chat a little bit less than right now, because I think it's more than one page is full of talking about Photoshop. Yeah. Try move it to off topic. There's a thread with off topic conversations if you want to hop in there. Just because it's a little bit distracting for me to like try to catch up with questions and whatnot. Okay. So the imaginary unit. Here's a fun little math problem. Okay, are you ready? I'm gonna give you a task. I want you to solve an equation. All right, I want you to solve this one. Okay, we have x squared. Sorry, I need to zoom in. X squared plus 1 equals 0. What is x? Can you find x in this case? Clearly, this might be a little bit of a trick question, but okay, maybe we can try to figure this out. Maybe we can go to Desmos, right? We have our graphing calculator, and let's go to a new one. And so we can just type this equation in. We can do x squared plus 1. So when is this equal to 0? In other words, when is the y value 0 of this graph? And the initial answer is it's impossible, right? You would just say it is never 0. We can clearly see that it only gets as close as this, right? It's 1 unit away from 0, and then it just shoots off into positive infinity, right, on both sides. So it seems like it's kind of impossible to solve this equation, right? But then some mathematicians said, what if we solve it anyway? What if we just invent a solution to this? So we can shuffle this around, right? We can say that x squared equals -1. We need to find a number where if we square it, in other words, multiply it by itself, it should become -1. This number doesn't exist in regular algebra. There is no number we can put here that solves this equation. So what we need to do is to kind of invent another algebraic symbol that can represent something that solves this. And so what that is called is the imaginary unit. And that is called I. So it's just a lowercase I. And there we go. Okay. Can't you use square root to take away the square from x on both sides? Well, then you need the square root of -1. And then you're back to the same problem, right? What is the square root of -1? Which is kind of the same issue. Generally, you can't do the square root of negative numbers. It's the same problem, but just expressed in a different way. And so we've kind of invented this symbol that just satisfies this formula. And what's really fascinating about this is that it kind of seems like it's just kind of this arbitrary concept. It's kind of like, okay, what's the use of this? Like, what's the point? But this is actually the entire basis for things like quaternions. This concept is central to make quaternions work the way that they do. It kind of just so happens that this invention turned out to be extremely useful in ways that they probably didn't expect when they begun like testing this out. And so you might wonder why, like how did this turn out to be useful? Well, let's explore this a little bit further. So this is the sole definition for the imaginary unit. So this is how we define the value of I. Okay. And so this is the thing about abstract algebra that is just, this is the abstract part, right? Like we don't really know what the contents of I is, and it's kind of beside the point. Like all we know is how it behaves when we square it, right? That's all we know. But then from this, we can derive a lot of like kind of interesting and weird properties. And so for instance, here's a question. Or actually, let's color code this. I think I should be purple because purple looks like mysterious and alien, right? I think that's a good color. Okay. So here's the question. What is I to the power of 3? What is that? Can we figure this out given the information that we have here? And it turns out, yes, we kind of can, right? Because we know that I to the power of 3, or I cubed, is the same thing as I times I times I, right? Which is also the same thing as I squared times I. Which we already know that I squared is -1, because that's the definition of the imaginary unit, right? So I times I is -1, which means that I cubed is simply -I. -I. And that's kind of weird and fascinating, isn't it? Or at least I think it is. And then we can go further. Let's go one step more. We have I to the power of 4. Do we know what this is at this point? Well, okay. So if we know that I times I equals -1. So clearly this has to be -1 times -1, right? Which that's just 1. And so we can continue doing this. We can also go the other direction. And so I don't know. We can let's add I cubed here, or I squared. This is the definition, so we know that this just equals -1. And then we have I to the power of 1, which that's just a regular definition, with something to the power of 1 is just that thing itself, so that's just I. Okay, cool. That's all neat, isn't it? Well, when we go further than this, that's when interesting things start to happen. And so if we then go further, if we do I to the power of 5, what is that? Can you make a guess what I to the power of 5 is? Assuming you don't already know the answer, but you should be able to derive it given all of this. I, yes. Because we know that I to the power of 4 is 1, and then we just multiply 1 by I, and then we're ending up with just I, right? And now you might be able to see that something fishy is about to happen. We can do this again. We can make a I to the power of 6, and the next one is going to be -1. We can do I to the power of 7, and we're going to go back to -I. Whoops, sorry. We can do I to the power of 8, and that is 1. And so you can probably see that there's a cyclic nature of this. The pattern for all of these repeats itself after 4 occurrences, right? And so this pattern is exactly the same. And this actually holds in the other direction too. So I to the power of 0 is 1. I to the power of -1 just, again, continues this pattern. And that's pretty fascinating, isn't it? Like, it looks like we have this kind of like circular or cyclic behavior just from this one definition. The only definition is that I squared is -1. And we now constructed this like algebraic construct that can make this repeating pattern. Okay. What about the in-betweens? We're gonna get to that. We're getting there. Okay. And so we can kind of like we can kind of think of this as a geometric concept. So what if you remember the number line, the real number line where we have all of our usual numbers, right? We have 0 in the middle, we have 1 somewhere here, we have -1 over here, and so forth, right? And then 2, 3, etc. So this is called the real number line. There we go. So that's the real number line, and that's all well and good. That's useful, right? But just like we did with vectors, we can actually just kind of add another coordinate system or another line perpendicular to that one. So I'm just gonna move things a little bit. We're gonna make it purple. We're gonna stick to the mysterious alien vibe of the imaginary numbers. And so this is the imaginary line. Imaginary kind of makes it seem more mysterious than it is, but that's fine. I forget if imaginary line is the correct term for this. Just pretend it is. All right, and so along this line, we have our values of I, right? So we have I over here, and then we have negative I over here. And then we can actually just kind of continue, right? Like we can multiply I by 2, for instance. So up here, we would have 2I. And so forth. So we can kind of like, we've now constructed a space of possible numbers. And this is called the complex plane. So we should probably move this one. All right, so the coordinate system we have here is the complex plane. Okay. And so we can actually define coordinates now. Because if we have a number, say we have 2 plus I. If we do 2 plus I, we can actually write that as a coordinate. Because the real number line, like 2, is the real part of this number. So 2 is going to be somewhere here. And then I is the imaginary part, and that's kind of like our y coordinate, right? And so that's going to be a point on the complex plane. And so we're kind of expressing this using both imaginary and real parts. And so you can actually kind of express them as a vector if you want. So you can actually write this as an imaginary vector with components 2 and 1. Because we're multiplying I by 1, right? So if you want, you can write it like this. Usually you don't do that though, and it can also be a little bit confusing because you might accidentally mix them up with regular vectors. But that actually gives us a point in this along this real number line. All right. So now that we can express points like this, then can you use I in Unity? Yes, C# has a complex data type. So this is called a complex number. All right. Okay, so this is kind of like a vector in the complex plane, right? We would just define this coordinate. And just like any other plane, we can just pick any number. We can pick maybe like this point here. So this would be like 0.4 plus 2i, right? And so this point right here, we can also express that. So any point in the complex space is very similar to vectors in that regard, right? Okay, but they have these weird rules. So let's think a little bit more deeply about these rules. Like how do they actually function? Well, we know that I to the power of 0. So let's add that one too. I to the power of 0 equals 1. most numbers to the power of 0 equals 1, so that's nothing special, right? And so I to the power of 0 lies here, right? Because if we think about this in the vector form, this is basically like writing 1 plus 0 I. So there's nothing on the imaginary component. It's just 0. And the same thing goes for this one. This is kind of like doing 0 plus I. So now we express these as complex numbers, right? We have a real part and an imaginary part. So these can be coordinates in this plane. So if we start at I to the power of 0, that is going to put us here at the, I don't know what color to use here. So maybe this is I to the power of 0. And then when we get the next point, it goes from 1, because again, it's 1 along the real number line and 0 along the imaginary line. And then if we do to the power of 1, we get I. And so what that does is that it's kind of like rotates it. If we get a number up here, and then we go for the next one, where the imaginary part is 0, and the real part is -1. And so that gives us a point right here. And so you can see that we're kind of cyclically moving like this. And then the next one is -I, so we're down here, and so forth. And so what's special about this is that this actually starts to kind of look like rotations, right? And so you might be able to already tell how this might be related to Quaternions, right? Because they work with they work with this type of cyclic behavior, just like rotations do. Technically, does that mean all numbers are imaginary because x equals x plus 0I? Well, kind of, but also kind of not. It's true that you can express any real number as a complex number, but usually there's no purpose in doing that. Like you can say that you can invent a number system that is called Wgarble. And then you're like, okay, I have these, like, I have invented a new symbol called Wgarble that looks like this. It's like an alpha, but it's rotated. And any real number can be expressed as 5 plus Wgarble times some number, like 7 or whatever. So like, yes, you can express every number as having 0 Wgarbles, right? But you don't really do that because it's pointless, because you have 0 amounts of Wgarble, right? And so what the so if something is on the real number line, you're Wgarble pilled. If something is fully on the number line and everything else is 0, we could just call that a real number, right? Like there's no reason to bring in the other things here. Okay. So it's more like you can express every number as a complex number if you want to, but usually there's context for that. Okay. All right. Okay. So, what's the formal way of saying it? Real numbers are contained within complex numbers. I think it's a subset. Yeah. Okay. But by the same token, like you can just say that they are a subset of the Wgarble numbers too. So it's just a matter of perspective and the purpose and the like reason you want to call it that, right? In the context of the complex plane, it's useful to still call these points complex numbers because we're still making use of the hacking Wgarble. You're not supposed to remember Wgarble. That's the least important part of this. Okay. Stop. It is slipping out of my control. Oh no. Okay. Anyway. Okay. Whew. So, someone asked, what about the numbers between? The numbers between have nothing to do with Garble, unfortunately. So what about numbers in between? We seem to have this like repeating pattern that kind of hints at some other relationship. Some incredibly smart people figured this out and actually found a way to traverse the complex plane in a perfect circle. In other words, they found a way to connect these absolutely perfectly. It is kind of hard to read up on exactly how that process went, but all you need to remember is that this was actually possible. And the formula for that, remember, we've been doing powers of I. That's kind of how we've been traversing this very basic circle, right? And someone figured out something really cool. And this has often been quoted and cited as one of the most beautiful formulas in mathematics. And I think I agree, because I think this is absolutely bonkers that someone figured this shit out. What they figured out was that if you want to figure out the point in this circle, then we want this to be a circle. So of course this has to be the cosine of some angle, right? So we're going to just be like, okay, this has to be the cosine of the angle. That's going to be the real number. And then we want the imaginary number to be the sine, or rather I times the sine of some angle, right? Like, this is what we want to solve. Like, this would give you a circle. This is literally what would give you a circle. Because remember, cosine gives you the x-coordinate, and the x-coordinate right now is the real number line. And the y-coordinate is the imaginary number line, so it should be I times that factor, right? Which should be the sine of the angle. And someone actually solved this, which is really cool. And so the solution to this is that if we take the mathematical constant e and raise it to the power of the imaginary unit times the angle theta, we get the solution. This is the relationship. And this is really weird that this actually works out. This is kind of wonky that we take this number e, and if you don't know what e is just a number like 2 point something something, and this is kind of the magic ingredient where if we take e to the power of the imaginary unit multiplied by the angle, we actually get this cyclic behavior. We literally get a circle. And so we can directly get the imaginary number on this circle based off of the angle theta. Using this formula. So we just take e to the power of I times theta, and that gives us a cyclic behavior. You might have seen this written in a special case. So there's a special case formula where usually you see this written as e to the I multiplied by pi, usually. So e to the I pi equals, or plus 1 equals 0. And this is called Euler's identity. And this, I think, is Euler's formula. Yes, Euler's formula. And this equation in particular has been described as the one of the most beautiful formulas in math, because it kind of involves all of the most important constants in math. Like we have e, we have I, we have pi, and we have 1, and we have 0. It's pretty wild that like all of this kind of conspire to create a circle in the imaginary plane. And of course, since I'm someone who doesn't like I, or doesn't like pi, I would rather express this using tau. So you can do this using tau as well. So using tau, it would be e to the I tau equals 1. Or if you really want to have all of these numbers in the same thing, then you can also just do -1 equals 0. And so this is Euler's identity. All right. And so this is kind of cool. And if you don't know what E is kind of interesting in its own right. So just to show an example of where E comes from, let's say you have a function f of x, and we are doing a constant a. We're doing a to the power of x. So now we have an exponential function. So let's change the range a little bit. Oops, that was not a good range. So this is just the standard exponential function. We have a number 1.7 to the power of x, and then we can modify this number here. So this is just an exponential fall off where we can tweak the first. We can tweak the base of this exponent. Now you might ask yourself, what is the derivative of this function? Well, we can let Desmos calculate that for us. So this is the derivative, the rate of change of this function. And then we can just kind of add the other derivatives, just the rate of change of the rate of change, the rate of change of the rate of change of the rate of change, and so forth. In other words, we have position, velocity, acceleration, jolts, and so forth. And so we can kind of just keep adding derivatives like this to our heart's content. And here's something fascinating that can happen for a very particular number here. Now watch these lines as we move this number around. Do you see what's happening here? They are all converging. And if we keep increasing, they're going to diverge again. And so it's kind of like, wait, why? What is this number? Like, why are they converging specifically at some weird like number around 2.7? Like what's up with that? Like we can zoom in a little bit more, and we can try to refine this and figure out exactly what this number is. This number is E. And so it's one of the fundamental constants in mathematics. So you have that here if you want to learn about E and how E works. And so what E is that it is the unique solution to the formula a to the x, where it is its own derivative, which is kind of weird. Like if you take the derivative of a function, you get the same function out of it. And e to the power of x is one of the few functions, depending on how you define functions, but it's kind of the only function that does this, which is very, very, very unique, with some exceptions, but we don't care about those exceptions. And so this is why e is a very like special number. And so e is not like I, where that is like a weird thing. E is just a number that is 2.71828, etc. Right? It is just a number. That's what e is. So like e and pi, both of them are just numbers. But I is not an algebraic number like this. So that's what e is. It's just kind of the magic constant where it is its own derivative. And so somehow this constant, where you have this constant that is its own derivative, if you raise that to the power of the imaginary unit times the circle constant, or an angle, you get this circular behavior. And that's Euler's formula, and this is Euler's identity. I have no clue how they worked this out. That math goes beyond me. I tried reading up on it quickly yesterday before today, but I couldn't quickly grasp it. Something related to the Taylor series and differential equations, I think. But yeah, and so this is the imaginary unit. Whew. Okay. That's that so far. Any questions? I don't know if I can answer too many questions about this because my knowledge about this is more limited than many other things. Where does Wagarble fit into this? I haven't quite figured out the algebraic properties of Wagarble, but we have to figure it out. How useful is it to have complex stuff to game dev? So mostly in game dev, this is only used for Quaternions. Nobody uses this for anything else pretty much. And if they do, they probably don't have to. Yeah, so this is almost only related to Quaternions. I don't quite understand the logic of how I squared, cubed, etc. repeats. All of that follows directly from this rule. So if you know that if you square them, it'll become -1. And that's it. From that, you can derive all of these numbers. Yeah. Okay. Yes, you will see the final notes. This is the final math lecture, yes. You're not expected to memorize all of this. That's why this is a bonus lecture. Explain this then. I have no clue why your colleague used imaginary numbers to solve that problem. That seems completely unnecessary to me. Okay, all right. So the reason why it repeats is because that's what happens from this rule. I'm not entirely sure how else to describe it apart from repeating what I already covered first. If you look at this equation right here, if you just focus on this one, if you take I cubed, that's the same thing as I times I, right? Which is the same thing as I squared times I. And we know what I squared is, right? We know what that is because that's our definition. I squared is -1. And so that's why we know that I cubed is equal to -I. And then we just continue to do this for the rest. So we just applied this rule over and over, and that gives us the answer to all of these. So that's why the more we continue the more we continue to raise this to the power of some integer, this pattern is going to repeat forever and ever. Because of the rules of how we multiply these numbers. Okay. All right. Is -I squared equals 1? Yes. Well, it depends on what you mean by if that negative is inside or outside. If you mean -I squared, or if you mean -I squared. Because these are two different things, because the squared has operator precedence. Okay. All right. Any other questions before we move on to a different type of abstract algebra? Ooh, I don't know if we should go on break. Maybe we shouldn't do break because we don't have that much time left. Okay. And so this whole idea can go pretty deep, depending on how far you want to explore this in various different corners. But in terms of game dev, again, this is mostly relevant to Quaternions. And so this imaginary unit, everything, literally all of the discoveries here, everything related to how e to the power of the imaginary unit times an angle in radians happens to follow a circle, Euler's identity, all of this stuff, everything is a natural consequence of this one definition. Everything. Like, this is just by trying this idea. Like, what if there's a number that we can square that becomes -1? Suddenly, all of this pops out of it, which is kind of like magic to me. It's pretty wild that this is even possible. And I think that is kind of fascinating. And so you can actually do similar things like this in different ways, and that has actually been done. And this is a very, very, very well explored field, the field of abstract algebra. And so you can make up other rules. So what if you make up another one? So for example, what if you say that we have this number right here that I've forgotten the name of? It's a Greek letter, I think. What if we say that this one squared equals 0? But here's a caveat. This value is not equal to 0. So now we've just kind of like invented another algebra. We just have this rule right here that we have some imaginary unit, or not imaginary. We've invented a new unit that when squared, it becomes 0. Epsilon, is this epsilon? Oh, maybe it is epsilon. And this is also a thing that actually exists. This has been explored. So instead of a complex number, there's a concept of dual numbers. So this is the dual numbers. I'm pretty sure that's the one that squares to 0. I just need to double check now. Just to make sure I don't... yes. Okay. Yeah, so this is called a hypercomplex number system. So both of these are hypercomplex number systems. And you can actually do this, you can keep doing this. There's another one where you say that, okay, what if we have something that squares to 1, but it's not 1? And then you follow the algebraic rules just to see what happens. Dual numbers happen to be useful for something called automatic differentiation. If you use dual numbers when you're doing like polynomials, dual numbers can actually help you get the derivative of functions kind of automatically, which is kind of neat, right? You can keep saying you can keep doing this as a mathematician giving out a threat. Yeah, be careful. Don't go too far. I'm not going to go too deep into the dual numbers. Again, there's another one where you can square it to 1. I forget what that's called. That's also apparently useful in some cases. But in either case, so this is a concept of making up a symbol, giving it algebraic rules like this squares to 0, but it's not 0. Like these kinds of things is something we can kind of just invent. And so maybe I can make up some rule for Wagarble that makes that a useful concept. Who knows? Maybe it's something like Wagarble squared, or Wagarble to the power of Wagarble is Wagarble. I don't know, and it's not 1. Okay. Are dual numbers the same as pseudo numbers or pseudo vectors? No. But we're gonna get to that later. Soon. Okay. All right. Let's continue. Or just one thing. I need to check my notification. Why does Unity even use Quaternions when Euler is easier? The only reason, like the one reason we use Quaternions is because they are computationally efficient. That's the only reason. There is no other reason. Quaternions are extremely annoying and complicated, and so they just kind of suck. It just so happens that they are very useful because they are cheap to evaluate. The power of Quaternions is that you can combine them to do you can combine them for composite rotations in a way that is both numerically accurate and they are faster to composite than any other method of rotation or any other representation of rotation. So when it comes to rotation matrices transform faster than Quaternions, but they don't composite as quickly as Quaternions. And so all of these different forms of rotation have their own use cases. And so if you consider Euler angles are kind of garbage too, because like you have this problem with gimbal lock and all of that stuff. But they're easy. Like it's easy to just punch in a number like 0, 90, 0. Like you know exactly what that means. And so we use Euler angles for like UI and to easily set up angles or rotations rather. But Euler angles have a lot of other problems. Compositing Euler angles is a nightmare. And by compositing, yes, I mean combining rotations, doing one rotation followed by another. Rotation matrices transform very quickly. They're very good at transformation, but they're stored in 9 numbers, which is a ridiculous amount of storage space, right? But they transform very efficiently. But they don't composite well at all. Axis angle is also very useful because axis angle allows you to go for like angles beyond 360 degrees. You can make this axis very long, and then you get like an angle like 5,000 or whatever, right? And you also get the axis immediately out of it, which can be useful in some cases. But this one does not composite well either. Doing composition using axis angles, as in this rotation followed by this rotation, is actually slow with axis angle. And so the only reason we use Quaternions is because they're fast. They are very fast at compositing. So if you have some Quaternions, Q, P, R, if you multiply these together, you get the same as if you're doing these rotations in succession. So you get a single Quaternion that just does all of these, right? So that's the power of Quaternions. Which is kind of wild that this really annoying, difficult representation happens to be the fastest way of doing composition. And also related to composition is also interpolation. Like pretty much all of these are garbage for interpolation, but Quaternions have very fast interpolation. So again, Quaternions useful for composition of rotations and interpolation. In other words, slurp, right? That's why we use Quaternions. Even though Quaternions are the most confusing, most unintuitive representation of them all, right? Okay. All right. Whew. I think we're ready to move on. All right. It's that little divider. Neat. we have now talked about some little bit of abstract algebra. But what if? Oh, we have a question. Why is it 360 for degrees? So I think we don't know exactly the historic reason for why this is, but I'm pretty sure it's because it's a, I think it's called a highly composite number. And composite means that it has many dividers, or specifically, it has more divisors than every number below it. And so 360 is one in this list here. I think it's even more divisible than that. Yeah, okay, here we go. It is called a a colossally abundant number, apparently. It is also a superiorly highly composite number. You can divide it by many things. That's what this means. So there you go. That's a useful number. It's not Wagarble though. Yeah, Wagarble is a whole different beast altogether. Okay. All right. I like if you have an emote for Wagarble. It looks like a cult symbol of some sort. All right. So, let's see. Where do we go next? Okay. So now, I'm going to talk a little bit how I lied to you in the beginning of our lecture. I lied to you when we were talking about vectors for the first time. Yeah, I'm sorry, I lied. Now that we have the perspective of the imaginary plane and the idea of using symbols, like abstract symbols, that we do algebra with, we've kind of already been doing that. I just haven't told you because it's kind of hidden and it's implicit. So remember, in the beginning of this lecture, or in the beginning of our whole math class, I talked about how we started with a number line, right? Where we have our numbers, -1, -2, 1, 2, and so forth. And then I said, okay, if we take this number line and just rotate it and create two perpendicular lines like this, then we get the Cartesian coordinate system where you know, we have our x-axis and the y-axis, right? So where we have our y-axis here, and then the x-axis here, right? That was kind of how we started this. But this is a lie. I actually skipped a step here that is kind of sneaky, that you actually don't really have to care about for the most part. Most people don't care about it and it doesn't matter. But when we have a vector space like this, just like we did for the imaginary numbers, remember how we could write this as 1 plus 0i. And this actually applies to vectors too. In other words, we have a basis vector, the x-axis here. This arrow is our basis for the x-coordinate. And this arrow right here is our basis for our y-coordinates, right? And so these two are units. Like we can call this x, or maybe we can call it x hat to clarify that these are normalized. And then we have the y bases. And so when we write a vector, like let's extend it a little further. When we write a vector like this, like we do a parenthesis, and we say a number like we have the number 2, and then we have the number 3. This is actually a shorthand. We're kind of skipping a lot of steps here. We're kind of just showing these numbers. And we pretend that like, oh, this is obviously this coordinate here, right? Because we have the x coordinate corresponds to 2, and the y coordinate corresponds to 3, right? But we can look at this from a different perspective. And that perspective is that what we're really doing here is that we are taking our basis of x and multiplying it by 2, and then we're adding the basis of y, and we're multiplying that by 3. And so there we go. And so just like how we could write imaginary numbers using our like invented units, we kind of do the same when it comes to vectors. We have this concept of a basis. So we have the x basis, and then we have the y basis, and then these are just the coefficients for each of these bases. And so this is really what we mean when we talk about vectors and doing operations on vectors. It's just that we kind of hand wave this. We kind of just pretend this isn't there, right? We just say 2, 3, and then you just have to know that they correspond to coordinates. And so why am I talking about this? Well, because when you want to define operations, this is where this starts becoming interesting. So let's say you want to add 2 vectors together. So we can just do, we have a vector here, right? And then we want to add another vector on top of that. And so let's pick some numbers that distinguishes it. So 6 x hat plus 7 y hat. And then if we want to figure out like, okay, what happens when you add vectors together, we can kind of just work this out, right? And so what that's going to end up being, and if we just treat these as like algebraic symbols, like, oh, we have x and we have y, then this is going to turn out to be, so 2 plus 6 times x hat, right? And then plus, so we have 3 plus 7 times the y-axis basis. So that's y hat. And so when we want to figure out what happens when you multiply vectors together or add vectors together or subtract vectors, instead of just like following some sort of predetermined math book of like, oh, this is how you add vectors, we can actually work out the math ourselves. Like, okay, well, let's just define 2 vectors this way, add them together, see what happens, and then we get the rule out of that, right? Like, oh, we notice that, okay, if we take a vector and add it to another vector, that means all we're doing is adding the components together, and that gives us the coefficients for each basis, right? So that's kind of cool, right? Like we have this new way of looking at vectors that can actually help us determine what certain operations do. And that also naturally kind of begs the question of like, what happens when you multiply 2 vectors? Because we've been saying all this time that like you cannot multiply vectors. It's just not a thing. Like you don't multiply vectors. We just have different types of multiplication. Like, oh, we have the dot product. That's one way you can multiply vectors. Or we have the cross product. This is another way you can multiply vectors, and so forth. And the reason for this is precisely because when we try to work out the math for multiplying vectors, we actually run into some trouble. And so I'm going to show you what that trouble is. I think first we can probably replace this with actual constants to make this a little bit more general. So we have a, and then we have by, now a cx, and then dy. Okay, so this is the formula for adding vectors together, right? So okay, so this is a little bit of a different perspective than what we were used to before, because before, again, we just kind of hand-waved it. We were just like, oh, you just do it component-wise. That's how it works. But now we kind of manually worked it out. Okay, so now the question is, what happens if we multiply this? Because we want to work out what multiplication means for vectors. Okay. So this is going to be a little bit messy. So I don't know if you remember how multiplication rules work, but we basically need to multiply these two together and then these two together and then add them all up, basically. Okay. Whew. So this is going to be AC. So far, so good. These two are just scalars, right? Like two numbers. So we have AC, and then we have X hat, right? X hat, but the other one also had X hat, so we actually have X hat squared. Okay, and then the next one, so this is A, let's see, A, D, X hat, and Y, whoops, wrong green. Y hat, so these are our bases, just remember that. And then plus. We're going to go through this. This is a long equation. All right, and then we have B times D, and we have, I'm taking a minor shortcut here. I hope people who are experienced doing this don't notice. Y hat and squared. Okay. And so now we end up with this kind of a mess, right? Because now it's kind of like, well, okay. So what does this even mean? Like what does it mean to square the basis vector, right? Like that's kind of confusing. What does it mean to now multiply these two basis vectors? Aren't we kind of back to square one? Because we don't know. Oh, what happened to BC? Oh shit, did I skip BC? I'm sorry. Maybe I don't like BC. Maybe that's it. Okay, so BC, it's a Y, wrong color, Y hat, I'm sorry. Y hat, X. Okay. There we go. All right. What was I gonna say? Right. And so this is kind of an unwieldy equation that has like lots of ambiguities, because like what does it mean to to square the basis vector, because then again, like, what does it mean to multiply two vectors? Or like, what does it mean to multiply the x basis by the y basis? And so here's where we can start adding a little bit more of a custom algebra. We can inject one little fascinating rule. So what if we define a new type of algebraic object for this? Like, okay, if we have two vectors like this, what if we just define a new quantity that represents the surface area that these two would form together? That represents this area right here. Like, what if we just invent a new type that is this area? And we're gonna say that is the type you get when you multiply two vectors together, like this. And so this will actually, I'm gonna skip a few steps now. I'm not gonna derive it all the way from the start because it becomes kind of circular. So this is called, we're going to call this a bivector. And so we have the concept of a number, right? And then we have a concept of a vector. And then we're going to add a new concept called a bivector. And that is going to represent this area right here. So if we multiply these two vectors together, we get a bivector that is this area. And so we're just going to say that x hat times y hat represents that area. And if you remember, this is where we're going to introduce the wedge product again. So if we do the wedge product between these two, then we get the area of this region, right? We've talked about the wedge product before. It is somewhere here. Here it is. Where if you have two 2D vectors, this is how you calculate the wedge product. And so this is the formula for the wedge product in 2D. In 3D, it is actually equivalent to the cross product, which I've lost. Here it is. And this would be the wedge product in 3D. And so there are a few things you need to note here. Bivectors in 3D have three components. They have x, and they have y, and they have z. But bivectors in 2D just have one component, which might be a little bit confusing. But if you, again, consider the area that they represent, that is the bivector. So we're just going to say that when you multiply two vectors together, that is going to be the wedge product between those two. And so if we know that that's going to be the area between two vectors, then we can kind of already know that, okay, what if we take a vector and we square it? What is the area that the span between two vectors that are exactly the same creates? What's that area? Well, the area of two vectors pointing the same direction, if you have a vector like this and a vector like this, you can see that the area kind of shrinks, and the more similar they are, the closer it's going to get to 0. In other words, if we square a basis vector, we get 0. At least using the wedge product. Okay. And so skipping a few steps. I'm going to skip ahead a little bit now. I'm not going to work it out all the way from the ground up. Multiplying two vectors. Let's say that we have a vector. I don't know if we should call it A because we already had a component there, but pretend this is a new thing. But multiplying two vectors together, A and B, we can actually define that as the dot product between A and B plus the wedge product between A and B. Okay, so this is kind of the core of geometric algebra. This is called the geometric product, and this is the default product when working in geometric algebra. I suppose there's a very obvious algebraic extensions of this with trivectors. Yes, there is. So this is the geometric product between two vectors. And so what's going to end up happening is that we can work out a bunch of algebraic rules so that this will basically boil down to the geometric product. So it's basically just going to be the dot products plus the wedge product. And so, yeah. Oh, sorry. Yeah, the squaring it doesn't become 0. It becomes 1. Sorry, I got that wrong. Squaring this one becomes 1. Because we can look back to the geometric product now. Like, what happens if you do A times A? That's A squared, right? Whoops. Again, I haven't taught this before, and so I'm a little rusty. So A times A would be A dot A. Wrong color. A dot A plus A wedge A. And we know that the wedge product between vectors pointing in the same direction is 0. And the dot product between two vectors pointing in the same direction is the squared magnitude, right? And so if it's the squared magnitude, in other words, the length squared, if these two are normalized, then it's just going to be 1, right? Because the squared magnitude is 1. And so that's why when we square a vector, we actually just get 1. Okay. So A hat squared equals 1. Okay. And so we can kind of see what happens here, right? If we have AC times x squared, then let's move that. Well, x squared is just 1. And so basically this just boils down to AC. And then plus A, D, X and Y, right? And then plus B, C, Y, X, and then plus, that's the wrong B color. Sorry about that. Plus B, D, and again, we have a square, so y hat squared is 1. And so now, if we rearrange this a little bit, we do some clever moves. Whoops, I'm being too clever. We just move this over here. This is the dot product, right? Like you can see that we're taking A, the x value, multiplying it by C, and then we add the y values multiplied together, so B times D. So this is the dot product, right? And then we have the rest of it here. And so what's happening here is that we have x and y, and then y and x. And if we look at the geometric product, how we deal with these two, it's the dot product plus the wedge product for these basis vectors. And the dot product between these two is 0 because they're perpendicular. So the dot product between this one and this one is just 0 because that's how the dot product works. If they're perpendicular, they're 0. So all we're left with is the wedge product. So we get x hat wedge y. And we also know that the wedge product is anti-commutative. In other words, A wedge B is equal to negative B wedge A, right? And so since we know that all that's left is the wedge product for these two, we can actually apply this rule to swap these. So we can if we just move these, just shuffle them around so that we have xy here instead, and then we multiply by -1 because it's, again, anti-commutative. So then we get negative there, and then we can factor out this, right? We can factor out the xy. And so now we can move this over here, and then we got a parenthesis, and here we're gonna get AD. Oops, this is gonna get complicated. I'm sorry, it all got very algebraic, but that's kind of the nature of this. So I hope it's somewhat understandable at least. It's very abstract, but that's why I saved this for last, because it's abstract. So now we can remove that part, and that's kind of neat. And so now we just factored that out. And so there you go. And hopefully you can see how this relates to the dot product and the wedge product. Because if you look at AD minus BC here, that is A, so the x component of the first one, times the y component of the second one, minus the y component of the first vector, and the times the x component of the second vector. And that is exactly what we had for our wedge product up here. That's what we're doing here. And so this is what happens when you multiply two vectors. However, now we've run into a very strange place, because now we have this construct where this is just a number, right? Like this is just a real number, like 6 or whatever. And this is a bivector, because we have this thing where we multiply these basis components together. And so this is where it becomes useful to try to think of something called a multivector. And this is kind of the mother of all vectors. And so this is the final boss. I hope you're ready. And so when we think about multivectors, then what that means is that we can define this giant vector that has all of the bases that we might need in our coordinate system. So in a 2D coordinate system, then the full extent of it is that we have a basis. So I'm going to do that in curly brackets. We have a basis of 1. So these are our real numbers, right? And then we have our x-axis, right? So this is our x-axis. We have our y-axis. And we have our, I guess we could go for a z-axis. I don't know. We can do both, actually. We can stick to 2D for now. And then we have the basis bivector. So we multiply these two together, and we get this bivector that represents the area. Remember, the area of this is a construct called a bivector that is equal to these two multiplied together. That's the basis bivector for 2D space. And then there's yeah, that's it. There we go. So this is the full multivector of two-dimensional space. And so when we have a vector, we only have values in these two, right? If we have a normal, just a straight up positional vector, like just the regular vectors we've been using all throughout this entire math course, we've been sticking to these two, right? And so what that means is that the other values are just 0. And then we just have some values here, right? And that means that we interpret this as a positional vector. But what's weird is that when we multiply vectors together, just like we saw here, using the geometric product, we now have a real component and a bivector component. And so when we multiply two vectors together, we all of a sudden have like some number here, like 5, and it's 0 for the basis vectors. And then we have some number for the basis bivector. So this is kind of the full multivector that contains all of these different bases. And this also, of course, extends to 3D. And so we're gonna do our regular old axis. I also have no idea how we're doing on time, but we're almost done with this. What? Okay, so we got our y hat, right? That's our y-axis. We got our x-axis. And we got our z-axis. Okay. And just a reminder, like I remember that I said that I lied to you earlier. And that's because I kind of pretended the x-axis is the same thing as the real number line. But when we're talking about geometric algebra, it's actually really important to make a distinction between them because these two bases are not the same thing. The real number line is actually perpendicular and separate from the x-axis and the y-axis. So that's why I said that I kind of cheekily lied to you, although not really, but you know. And so real numbers exists independently of our vector representation. All right, okay. And so for 3D, so this is the 2D multivector. So for 3D, we actually have a little bit more. So for 3D, we have our real numbers. That's a basis of just the number 1. And then we have our x-axis. We have our y-axis. We have our z-axis. And here's where it gets a little bit interesting. And here's where people will fight over how to how to do these basis bivectors. But remember, the bivectors represent an oriented area. This is a little bit of an abstract concept. It took me a very long time to wrap my head around this. But I think that the easiest way I can explain this is that when you have a normal vector, the position of this vector is kind of defined using projections. If you project this to the y-axis, or you project it to the z-axis, or the x-axis, we kind of get the coordinate of this object, right? It's a little bit hard to draw these. So all this is kind of like we're taking a 3D point, projecting it into 1D, and then we get the distance here per axis. Now imagine doing the same thing with a shape or an area. So let's say that we draw some sort of area here, like a plane, right, with some orientation. just like we projected a point, we can actually project this area. Like, what would the shadow of this shape be against this plane here, the plane formed by the y and z axis? And this projected area that we get here, it will most likely be kind of a slim rectangle, right? I'm going to draw it in red. So this would be the projected area for this plane, right? We can project it downwards as well. So if we project it down onto the plane here, that would kind of be the shadow of that plane here as well, right? And then we can project it against the z-axis or the z-plane, which is this plane right here. And this is going to be like a very thin one. It might actually be exactly 0. So that's going to be a very, very thin shadow projection there, right? Okay, so a bivector is expressed just like a vector is expressed using projected distances along each axis. A bivector is expressed using the area of each of these regions. And so you can express a bivector using a vector 3. Like you just use that as a container to specify all of these areas, right? So we have the area here, the area x, an area z, and area y. So we kind of split it up into its components, just like we did for vectors. So we have area x, and then we have area y, and we have area z. But we need to remember that this is not the same thing as a position vector. Again, this is an oriented area. And what we mean by oriented is that it can actually point in both directions. If you remember the normal vector, these areas can be signed. And so the normal of this plane can actually point in both directions. And they are not equal. So we can actually mirror this plane if we want to. And so this is what a bivector is. And I don't know how much I separated this to a separate layer, but and so we're kind of projecting these onto the planes here. I hope that analogy made sense with the shadows. This concept is really abstract. Again, it took me several days to get this. So don't worry if you don't get this immediately. Okay, so we have our basis vectors, and then we have our areas, our oriented areas here, and these are our basis bivectors. And so this is x hat multiplied by y hat. So this is the same bivector we had in 2D, right? But then for 3D, we have two more basis bivectors. We have this plane right here. And this plane is y hat times z hat. And then finally, we have the bottom plane here. And the bottom plane is the basis bivector from z hat. And yes, it starts with a z. If you read a blog post that starts with an x here, they are objectively wrong. And you should never ever do xz here. So fuck those people. Okay? And so these are our basis bivectors. In our 3D, multivector, these are the basis bivectors we have to work with, right? And the order of these three is kind of up for debate. Geometric algebra, especially in game development, is very much in its infancy. We're kind of starting to explore this at this point, but it's not something that's been established at all. And so a lot of these things haven't been worked out, like what order these should be in. My opinion is that we should start with YZ. That YZ should be the first one. It doesn't really matter which order you write them in, as long as you're consistent within your application. But if you want your application to communicate with other things, it might be important to get this right. Yeah, so YZ, and then Z, X. And then finally, the one that we have in the 2D system, which is XY. And there we go. Need to scoot this a little bit. Oh no, layers. Okay. And so now we can also add a third one, which is we're kind of taking the same idea and extending it one step further. And this is where we get the volume of this. And that is called a basis trivector, which is kind of rarely used. So the basis trivector is, of course, X, Y, Z. And there we go. This is the full multivector for 3D geometric algebra. And so there we go. It's a bit of a mouthful. And I need to organize my notes without moving everything to hell and back. Okay. This is geometric algebra. Look, we actually covered geometric algebra. And now we can like drop some cool facts about geometric algebra. Here's it's 4 p.m. on a Friday. Yes. I'm gonna go for a few more minutes. I hope you don't have to run off to anywhere. There are a few more things I want to talk about because I'm excited about this and it's interesting. But if you really have to like go pick up your kid and they're like screaming at kindergarten and they really want you, then feel free to leave. Again, this is more of an optional last thing. And so wait, are you criticizing my diagram? Are you not liking this? Yeah, well, you're wrong. Okay. And so one thing that's pretty cool about this is that this multivector, like you can write a vector containing all of these numbers. Like you write arbitrary numbers in each of these. So what's kind of cool about this is that this geometric algebra, like we've kind of like sort of invented this whole separate algebraic system. What you get if you take this one, like the real numbers, the real number line, and if you take the xy plane right here, this, if you use only these two components, that's complex numbers. So just straight up using these and these, you have the same definition as complex numbers. And that's kind of wild. Like if you have x hat and y hat, and you square this, you have -1. And this is exactly the definition of imaginary numbers. And so you actually have the behavior of imaginary numbers can be directly encoded in this type of format using bivectors. And so the imaginary number, we could also just call that the basis bivector. And that's kind of weird and pretty cool. And the same thing actually goes for Quaternions. If you take the real part here, so we have the real numbers, and all these three, this is a Quaternion. Usually, you would call these I, J, and K, but in geometric algebra, they're just basis bivectors, right? Because all of these square to -1. And so this has actually encapsulated the entire behavior of Quaternions. And then what about vectors? Well, vectors is just these three, right? Like if we just use these, we have our regular old standard vectors. And so this is just a way where we can sort of generalize a lot of these concepts into one framework that makes it very consistent and portable and actually scalable to any dimension. Yeah, and I think that that's a pretty interesting fact, that just because you start defining this new geometric concept of a bivector, all of a sudden you actually encapsulate a lot of the things we already talked about, like imaginary numbers and vectors in 3D space and quaternions. Like we just do that, right? And so what a quaternion really is it is a construct that has a real number, the real number line, and it has three types of imaginary units. There are three separate imaginary units, but so that's part of quaternions. And the whole concept of a quaternion is that the three basis bivectors actually define a plane, right? Because again, a bivector is an oriented area. It has an orientation, and the magnitude is the area of that plane. And then we have the real part of a quaternion. Then what the quaternion does is that it encodes trigonometric properties in the real part and the magnitude of the basis bivectors, or the bivector part. And then it can basically reconstruct a rotation around that plane using that information. And the way that it's algebraically set up just so happens to be in a way where if we multiply quaternions together, it's like taking one rotation and then doing the other one. When you're doing quaternions, but expressing them using geometric algebra, they're usually called rotors. So you're going to find this term. If you're searching for geometric algebra and rotations, then rotors are going to come up. And so rotors are basically a multivector that contains the real part and the bivector parts. And then using those, we can multiply them together to kind of stack rotations. And so that's how you get quaternions from geometric algebra. All right. There we go. That was everything I just had to word vomit out. It's a lot to talk about, and I hope it wasn't super duper confusing. You can sort of think of this as an introduction to geometric algebra. Yeah. Any questions? Was that like 100% super duper clear? Do you feel like you have 100% grasp of geometric algebra at this point? I'm not expecting you to. I haven't had any water or anything to drink for like the past hour. I don't have enough grasp to ask questions. Yeah, that is expected. Usually you kind of have to read up on this a lot to kind of wrap your head around the concept. It's usually pretty difficult. Yeah. It's also kind of esoteric. Right now, the geometric algebra is like very, very slowly making its way into game development. Mostly the idea of geometric algebra has mostly been used in people making like four-dimensional games, because geometric algebra actually extends to any dimensions. So it's a very general concept. Yeah, and it's actually kind of interesting if you consider the number of components for each of these constructs, for the bivectors and trivectors. Then does 4D games exist? Yes. Someone is making a 4D golfing game, and then there's another game called Miyagakure, I think, which is a puzzle exploration game. Very experimental stuff. Yeah. I forget all of the four-dimensional games. But I think the biggest thing about geometric algebra in games is that you can basically replace quaternions with rotors, and it's just the same basically. It like quaternions and rotors are just different ways of describing the same thing. The math turns out to be exactly the same, and there's not like any, yeah, you don't actually there's no difference apart from the perspective that you're viewing them. Okay, so I think this is one of the games. Yeah. Yeah, this one. So this is a 4-dimensional game. I don't know if they use geometric algebra for this one, but it's a puzzle game where you can basically shift the world through the 4-dimensional space, or through the fourth dimension, which is an axis perpendicular to the other axes, right? And it's very hard to wrap your head around about what the fuck is going on when you're doing like 4D transformations like this. But it is a game that has concepts from 4D. And so there you go. That's a puzzle game. That's a 4D game. And then there is a 4D golf game. I forget what it's called. I think it's this one. Yeah. So this is from a fellow YouTuber, Code Parade, that they're making this 4D golf game. And so you can kind of you kind of get this projection of the 4D space into 3D. And so you can kind of warp and view things from different angles, right? And so when you're making a game like this, the way that you represent geometry and angles and literally everything gets really complicated. As you can see, it's very, very hard to even see what's going on. It is very trippy, yeah. Because our brains are not very good at interpreting 4D space. But yeah, so 4D games exist. They are rare, and it's mostly people who are really excited to do some incredibly esoteric math. Okay. Yeah, so 4D games. Imagine that. Okay, we didn't super dive into the black box of Quaternions. We barely scratched the surface. We've just like explored imaginary numbers. And so Quaternions. So Quaternions, they are kind of they encode angle axis effectively. It's a special encoding of angle axis. So if you look at the Quaternions, the IJK here, those are equivalent to the bivectors here, the basis bivectors. So each of these square to -1, just like imaginary numbers. And they have some fascinating properties. And the whole thing that they're useful for is rotation. And rotation is done by taking your quaternion, multiplying it by your vector, and then multiplying it by the inverse of that quaternion, or the conjugate, which is a little bit faster to compute. And this is called a sandwich product, which is going to come up a lot if you're reading about geometric algebra or, geometric algebra or quaternions. Yeah, and they're, for mathematical reasons, they composite very well. In other words, rotating something by one quaternion and then another quaternion is the same thing as multiplying those quaternions first and then rotating the vector by that quaternion. And so yeah, there are many different ways you can try to interpret this. I can share this with you if you want. If you want to read up on quaternions, there you go. These are my own notes. The picture is not my own, but yeah. Why is there a garble taking over the okay, all right. I think that is all I wanted to talk about, I think. Do you have any questions? Anything else you want me to chat about while you have me? Because this is the final day. I am leaving soon. Well, very soon. Do you have any thoughts or questions about the whole course and lecture and all of that stuff? It is the end of your lectures. Yep. No more math. You no longer have to suffer through all of this. Just a screen full of numbers and symbols. Will you still be able to answer some questions after this? Depends on what type of questions and how long after. This is the end of my time with FutureGames here. And so after the lecture, I'm not gonna be on the clock, so I'm not gonna be available for guidance or whatever. Answer questions like tomorrow or next week. I usually vaguely hang around in Discord, so sometimes I will, but I'm not gonna get paid to do it. So, but usually I will still exist and do a little bit of answering, but don't expect me to answer quickly because I'm gonna be doing other things. Aren't you gonna teach us shaders in December? Oh yeah, I mean I'm gonna do your shader course as well, but now we're not doing shaders right now. So now this is the end of the math course. So, can we pay you in candy? Not really. No, I'm sorry. It doesn't work that way. Okay. Well, if there are no further questions, then I guess that's it. Now you know Quaternions. Yes, all of these streams are going to be on my channel. So if you want to rewatch anything, you're very welcome to do that. Yeah. If you, I guess, oh, here's a way you can pay me. If you can crowdsource timestamps for every topic on the YouTube video, because it takes a long time for me to go through every video to find like, okay, this is where I start talking about Quaternions. This is where I start talking about the first assignment and so on. So if you want to crowdsource the timestamps that I should put in the comments of the YouTube video, that would be valuable. But it's kind of tedious and boring. Okay. Yeah. Thanks for having us. It's been informative. Oh yeah, no worries. Are you allowed to advertise your products? Well, I mean, technically, I've gone overtime and I'm outside of the lecture hours, so I guess I could. But do you want me to, or are you asking if I've already broken the law by talking about shapes, or are you just curious about shapes? Or thank you for teaching us. No worries. I'm happy to teach math. And I hope it'll be useful. I know this course is very intense. If you're pretty new to math and a lot of these things are like completely new to you, or you forgot everything from like high school, we've basically been speed running math from like first grade to late high school in like 6 days. So if you feel like this is overwhelming and there's a lot to learn, that's normal. It's totally okay to feel like this is overwhelming. And then on top of that, there's everything related to like programming and data structures and all of that stuff that I'm kind of just like presuming that you know. So just keep in mind that this can be overwhelming, and it will be for many people. Yeah. But yeah, I hope this has been valuable. I can also show a little bit of shapes if you want to see it, as part of not the course, but just as a human being sitting in front of your computer or in your computer. If you're interested to see what shapes is, I've been talking about it a lot throughout this lecture, I guess, or yeah, lecture series. learned more math in 2 weeks than I did in 12 years of school. That sounds great. I'm so happy to hear that. I'm glad it's been that useful to you. Oh, okay. Never wrapped my brain around most of this in high school because I never did anything practical. Yeah. That's usually the problem I have with it as well. It's usually like, well, why am I gonna need this? After WGARBL, everything started to fall in place. That's good. I'm so happy WGARBL could do that for you. I still have to work out the algebraic properties of WGARBL. So I'll get back to you once I know what the definition of WGARBL is. Okay. I should save this. I'm gonna stick around for a little bit longer. You wanted to see shapes, so I can show you shapes if you want to. I'm just gonna export this image. This is taking a while to load. Come on. Come on, save for web. I believe in you. Excuse me. Well, I guess I can start using shapes while Photoshop is thinking. Where do I... Do you feel more confident to hold an online lecture rather than inside a classroom? I hate using shitty school computers where the monitor is like 30 FPS, has shitty color, and the mouse is like lagging, and the keyboard is bad, and I don't have my shortcuts, I don't have my applications, I don't have anything that I'm used to having, and it feels like I'm using like some sort of alien workstation. I hate that, and so I love to do remote teaching because I have everything set up exactly the way that I want it to be, and so yes, I love doing it remote. So yeah, and so doing it like on site is going to be a strictly worse experience, except for interpersonal stuff, like for hanging out, for the like mingling and getting to know each other and reading the tone of questions. Like anything like interpersonal is easier when you're on site, but yeah, but the teaching itself is much easier remote for me. Okay, how did Photoshop manage to... Oh yeah, there we go, cool. This is a very large file. It's 11 megabyte. Would you also bring your cats if you were allowed into a classroom? I don't think I'm allowed, but let's say if I was allowed, maybe. The problem is that they would have to get used to litter boxes in a new location. Maybe. If the classroom had a litter box, then yes, I would do that. Yeah, I think that would be the biggest issue. Otherwise, I think I would bring them because I've gone for walks with the kittens, and so they know what it's like to not be at home, at least. Okay, so this is just gonna take ages again, but I can show you shapes. Let's talk a little bit about shapes. Why not? Gonna create a new scene. Oh, I have my math library and everything here. Hell yeah! Now I'm fully at my full capacity. Finally. Let's fix the lighting. This is a bad lighting situation. There we go. All right. Yeah, what do we want to do with shapes? What do we want to draw? Um, okay, just to show a basic thing. With Garble, you know, should we draw with Garble? Okay, we should. Do we work out the equation for Garble first? Okay. Oh shit, I flipped it. What just happened in chat? Or in the Discord? That is unreadable. Why is this not working? Oh, because there we go. Okay. I think we can just do this with just trig functions, right? It might take a while. I don't want to get stuck on that. Let's look at shapes instead. It's more fun. Wait, why is my formatting not working? Oh, maybe because it opened in the same writer? Yes, shapes will go on sale very soon, I think. Shapes is gonna be part of a humble bundle. And so it's gonna go on there. So yes, it's gonna be on sale. Okay. And so here, let's do some shapes. My favorite way of drawing shapes is using a thing called the immediate mode shape drawer. Which is kind of similar to onDraw gizmos, but better. And so we have a function called draw shapes. And then we set up a new draw command to draw in our camera. Then here we can draw whatever we want. So we can maybe do draw.matrix equals transform local world matrix. This you recognize. We did this in Gizmos as well. And then what do we want to draw? Maybe we want to draw a ring. We want to draw it at 0. Maybe we want to draw it with a oh right, the rotation. I guess we can just do default rotation. And then we'd set a radius to 1, and we need a thickness, so 0.04, something like that maybe. And so then let's also mark this as execute in edit mode so that we can see it in, or sorry, execute always. That makes it visible in editor. So let's recompile. And there we go. Look at this shape. And so in shapes, you can specify thickness, and it actually has anti-aliasing. There's no shitty pixelated garbage things that you usually get with like gizmos or handles or whatever. So this one actually looks kind of clean and nice, right? So what do we want to draw with this? Maybe we want to draw a line from vector 3.0 to a new vector. Excuse me. Angle to direction, and maybe we can do a time dot, real time since startup. Okay, now we should have a spinning line. There we go. Always refresh. So this is a line. It has a rounded end cap. We can also make it look different. We can make I don't know. We can make it look whatever we want. We can also fill this circle. So maybe we want to have a little bit of a background color. So we could do just pass a color in here. What? And then this is going to be a disk with no thickness. I think we can also skip the rotation for both of these. So this is a fill. This is a border. So recompile. Now we're going to fill the background. And so we're starting to create a thing with it, right? And so you can. This is kind of what the library is, and it also works in 3D. So you can draw things in whatever space you want, and however you want to draw it. All of my videos are made using shapes, so we can draw like polylines and stuff as well. Yeah, lots of things you can do with this. But this is basically the what the API looks like. You cannot draw in 4D now. Then it has a bunch of different functions. You can draw rounded rectangles. You can do dashed circles. It also has a component-based API, so you can make a. So let's say we want to draw an arc. So we can increase the radius, change the thickness. Maybe we want this one to have rounded caps. Maybe we want to have a dashed arc where we set the number of dashes to some value. Maybe we want rounded dashes. So there we go. Then maybe we want to change the thickness a little bit again. Maybe we want to offset the dashes so we can animate this over time if we want to. We can, yeah, lots of things we can do using shapes. Just has a bunch of features like this. You can set the end angle, the start angle. It's very flexible. And so anytime you want to do vector graphics in Unity, then there you go. This is a way you can use. Yes, this is basically vector graphics. There's no aliasing because I made the shaders so that they don't have aliasing. Yeah, I have anti-aliasing baked into these shaders themselves, and so yeah, and so this entire concept, this whole way of working, this is how I made my Bezier curve video. I don't know if the Bezier curve video actually runs anymore because I have changed a lot of things since then. But like this whole video is also made using shapes. And it's all animated in Unity and drawn using shapes. And I have this like custom animation tool that I have for doing these types of things. So in this case, it shows you how to get the bounding box of a Bezier curve, which you can do if you analyze the derivatives. Which is kind of neat, and then you find these extrema, yeah, and then showcasing the derivative and whatnot. All of this is drawn in shapes, and it's animated in code for the most part, and yeah, so this is all just like scene view shenanigans. It's all drawn in real time. So I've been doing a lot of vector graphic style drawing as of late, to animate and do all of these things. Okay. And so that's shapes. You can draw vector shit. And yeah. Here's my outro. See, it turned 3D. Isn't that neat? The 3D capabilities of shapes, as in drawing like volumetric shapes, is a little bit more limited, and that's where you have a little bit more aliasing, because there's just no way to do anti-aliasing for 3D shapes. That doesn't like tie into the render pipeline in a way that's going to be a nightmare. Yeah. Is it bad if you run a lot of this every? So, I mean, it's not going to be super expensive, but it all depends on how you set it up. Oh, I broke the code for this. Oh no, they're slightly borked. But yeah, you can definitely use this for AI, but yes, you have to run it every frame, especially if you use at least if you use the immediate mode. You can always use the components themselves if you want to, but yeah. Beautiful. I like how we have a billboarded polyline for the credits, as if I needed it to be billboarded. Okay. Sheeps. So Spline video is the one that I'm currently working on. It's like all of this is also still animated in Unity. Just there's no, I don't have any pre-rendered animations. It's all real time. This is taking so long to make. I need to release this soon. I've spent so long on this. Like a ridiculous amount of time. And then I got burnt out, and I still haven't fully recovered from it. And so it's like, I'm like at the end of this video. I'm like almost done. I just have like 2 or 3 things I need to do before I can call this done. But almost there. Salad is the best contributor because he is large. That's true. Yeah. And so all of these animations are set up in code. So you can actually see some of the easing functions at the bottom here. We talked about easing functions today, right? If you look at the 3 functions here, you can see that there's like some cascading curves. There are 4 of them, one after the other. That's triggering this animation here. That's each of these 4 that's animating out over here. And the whole video editor is fully predetermined. Like all of this is directly set up where every point in time has a specific value for everything that happens. And so I don't have to simulate anything. I can jump to any point in time, and everything knows what state it should be in. And so it's a very nice way of setting things up, because I can freely change time however I want. It's not like it takes time to reverse. I can literally set the playback rate to -1, and I'm gonna play the entire video backwards, right? Because I don't have a concept of like simulating anything. Yes, everything is dynamic. There is nothing that is like, yeah, there's no dynamic systems in this. Although I have been wanting to add some dynamic systems, because there are a few things that are hard to do like this. But yeah. Continuity. Would you say that has cut down on time or increased, like having code-based animations and stuff like that? I mean, I wouldn't be able to do these things without code-based animations because all of these have to be mathematically accurate. Like if someone told me, oh, just freehand the curvature curve for this Hermite spline, I wouldn't be able to do this, right? It has to be code-based. But in terms of just the animations, apart from the drawing, it would maybe work, but I feel like it would be tedious. I started doing a workflow like that at some point, but the problem is that a lot of video editors and animation tools are not made for ripple editing. In other words, if I want to make one animation a little bit longer, in most video editors, you have to like select everything to the right and then move it a little bit. Or if they have built-in support for ripple editing, you can use that. But the way that I set up my animation tools, everything is ripple edit by default. I can insert an animation anywhere, and I don't have to care about everything that comes after or anything that comes before. Every animation, I can just insert something, and everything ahead is just going to shift automatically. And so it makes it very nice in that way. Yeah. I can show you what the animation code looks like if you're curious. Ooh, this might be the most horrible of them all. So let's open the horrible one. Production code, right? I have a million functions here. So here are separate animations. So I have animations in every script. And so this is what my animation looks like. I like label a section just to make it easier to navigate. And then it's basically, I say show this value animated from 0 to 1 over 0.6 seconds with this easing function, and then wait for that to finish. Then animate show curve index 3 over 0.6 seconds with an easing function out 3 to 1. Show means animate to 1. And then I pause for 1 second, and then I show a cascading range of point labels. So cascade means that I show several things one after the other. And then I just give it a range from index 7 to 13. I use an easing function on all of those. And then it's just kind of, this is the animation. This is the animation data for the entire video. And so the timeline that you see down here, this timeline is literally just for previewing those animations. So I don't do the animations in the timeline. That's just for previewing. And so the so like for example, the point labels here. So point labels is something that I show a lot. So you can see that these points here, they appear one after the other, right? So this is a cascading animation. So that's just a helper function I have to do this like reveal of many things one after the other. And I do that a lot, like in many different places. And so the here's an example, another animation where I reveal one thing after the other. So you can see here, just doing like the lines and the points appearing. Also set up the same way, just do this cascading animation, and so forth. Yeah. Oh, I should release this video. I've been working on it for way too long. Goodness. Okay, anyway, are there any other last final questions before I go? I'm starting to get my streaming headache as usual. So I'm gonna have to stop streaming pretty soon. It's like what programming is actually for, like making tools to help you do what you want easier. Yeah, quite literally. The whole, yeah, all of this is very much just because I needed to do code-based animations, and there was no like existing tool that was good for me. And everyone was always like, oh, you should use 3 Blue 1 Brown's editor. And I'm like, no, I don't want to use Python. And also, mine is real time. 3 Blue 1 Browns requires rendering. Fuck that. I want real time shit because I'm a game developer, and so I made my own editor. And so here we are. Yeah. Okay. I want to ask what app you use for taking notes. Oh, Notion. It's the same one I used for everything I sent you. So I've been using Notion, which is useful. I use it for everything. I have a lot of notes on many different splines. Notes on math notation, notes on trajectories, a lot of notes on trajectories. Yeah, quite a lot. I also have my notes for D&D, for our D&D campaign, also important to have. Gotta have some roleplay notes and combat notes for things to remember. My reckless casting that I also had in D&D was also good to remember. Good things. I just have lots of notes. And obviously the notes we had for this course. So the all the lectures are here, also through Notion. Not all notes are available. Some of them are just personal. And so some of them are available and I link them. But not all. Do you have any tips on how to repeat everything you've lectured so far? I honestly don't really know, apart from like either rewatching if you feel like you've forgotten a lot, or if you didn't finish the assignments, you could do some of those assignments. You could also, of course, just take other classes. Like, I know 3 Blue 1 Brown has a linear algebra series. You can watch that if you want to brush up on that. Yeah. Okay, I wonder if Photoshop is done saving the image. I think it might be. Oh, yeah, there we go. All right. Yeah, my brain is also mush. We covered a lot. We did it. You are now prepared for the world. Any other questions? Any last thoughts? How's YouTube chat? How are you doing, YouTube? Sorry, I haven't been paying too much attention to your chat. Excuse me. All right. I guess we're good. No more questions? Can you share the math scribbles? Yes. I'm not sure if I should post it publicly. I'm conflicted on that. Because I've had a lot of people ask me to make a proper poster out of this. And so I've been considering doing that and like putting up a store where people can buy a clean version of this, like an actual poster. But if I release this publicly, what if someone just takes it? And then I'm not going to get my capitalism money from them buying the poster if they just steal the high resolution version of these notes. I don't know. I don't know. So I need to. I don't know if I wanna publicly release it. But I think if I do a proper cleaned up version of this, then I think it would actually look substantially cleaner than the absolute chaos that this is. So maybe it doesn't matter. Maybe it's okay if people print the shitty version. I don't know. NFT poster. I will not be able to do it before Christmas. I have too many things ahead that I'm already stressed about, unfortunately. So, um, okay. But yeah, I should share this publicly. I will do that. Use AI to upscale it. Oh God. Okay, I have to cut the stream before the 4-hour mark, and we are almost there. So this is probably a good way to stop. A good place to stop. Then I guess that's it. If you want the last bits of kittens, Thor is in the box. Right there. That's Thor. Uncle Thor. And then we have the kittens. They're in each goblet of that tree. We have toast in the top and then salad underneath. So just say goodbye to the kittens. Thank you all for joining the math course. Again, hope it was good. Hope it was useful. And for any other like FutureGames students outside of FG22, I hope you got some new information that you found useful. All of these are gonna stay on YouTube, so you can just go to my YouTube if you want to rewatch these. Otherwise, thank you so much for having me. It was fun, and I'm sorry if I went too fast for things, and I'm sorry if I panned the camera too much in Photoshop. I know some people get annoyed by that. But yeah, all right, everyone. Thanks, FG 22. You've been great, and I will see you all during the shader course. And otherwise, I'm just gonna hover around a little bit in Discord every now and then. But yeah, bye everyone. Good luck with all of your future assignments and future games. See, I did a pun. All right, bye everyone.